Hi, I'm Mitch, and this is my submission for video 1 for Phys2101, and I am answering the question of how nuclear and radiation physics have impacted my life. Okay, so there's something you should know about me, and that is that I love dinosaurs. I've always been interested in them, and one of my most prized possessions is an extensive fossil collection containing dinosaur fossils from many time periods. Now, something that you might be wondering is, how do we know how old a dinosaur fossil is? Well, there are a few ways this can be done, but the primary one is radioactive dating. Now, the most well-known form of radioactive dating is carbon-14 dating, but that really only applies to rocks under about 50,000 years of age. Much older than that, and there is far too little carbon-14 remaining in order to reliably determine the age, due to the short half-life of carbon-14. So let's look at two other radioactive dating methods. First, there's potassium-argon dating, where potassium-40 decays via a minor decay pathway to argon-40 through electron capture. Now, potassium-40 has a half-life of about 1.25 billion years, and so it does not have the issue of there being too little remaining to determine the age of the rock. Now, back to electron capture. Electron capture occurs when an electron in one of the inner shells of an atom is absorbed into the nucleus, reacts with a proton, producing a neutron and a neutrino. The neutrino is emitted, the neutron remains. In this case, this results in potassium-40 being converted into argon-40. Now, this really only works as a dating method for igneous rocks, because when a rock liquefies, all the argon escapes and then solidifies, making it an igneous rock, there will be no argon contained within it, meaning that any argon found within it later on must be the product of potassium-40 decay. Okay, let's move on to the other dating method, which is uranium-lead dating. Now, uranium-238 and 235 have half-lives of about 4.5 billion years and 0.7 billion years, respectively, and so also don't have the issue of a short half-life. And they primarily decay via alpha decay, successive alpha decays, until they finally reach a stable nucleus, specifically lead-206. Now, what is alpha decay? Well, alpha decay is the emission of an alpha particle, 2 protons and 2 neutrons, from the nucleus of an atom. And alpha decay usually occurs when the nucleus grows so large that the Coulomb repulsion between the protons becomes stronger than the strong attraction that usually holds the nucleus together. Consequently, after successive alpha decays, you obtain a lead-206 nucleus, and then by examining the ratio between lead-206 and uranium within the rock, it is possible to determine its age. However, this also really only applies to igneous rock, because when rocks liquefy, zirconium crystals also are broken, and then when it resolidifies, they reform. But due to the suitable size of uranium atoms, they are able to be incorporated into the zirconium lattice structure. But lead is not. Consequently, any lead that is then later found within the zirconium crystal structure must be the product of uranium alpha decay. Okay, now we've got a bit of time left, so we're going to quickly cover the stellar origins of potassium-40 and uranium. Potassium-40 almost exclusively is formed within very high mass stars, specifically those of greater than about 8 solar masses, where it forms via successive alpha captures from light nuclei, like carbon-12, up to calcium-40. Alpha capture is where an alpha particle is absorbed into the nucleus. Okay, the calcium-40 that is then produced via this process can then undergo beta plus decay to form potassium-40. Okay, let's move on to uranium. Uranium is an R process element, and that means it can almost only form when the R process occurs, which happens under very high neutron flux, which primarily occurs when neutron stars merge or in some core collapse supernovae. So, a lighter nuclei will be bombarded by neutrons, undergo neutron capture many times, and before it is able to decay, and then, when it is very heavy, it will undergo successive beta minus and alpha decays until it reaches a relatively stable nucleus, like uranium. Okay, so that's the origins of potassium-40 and uranium. Let's quickly summarize. We have discussed the impact of nuclear physics on my life through its applications in the field of paleontology due to my interest in dinosaurs. Specifically, we discussed potassium-argon dating and uranium-lead dating as methods, as well as the origins of potassium-40 and uranium. Thank you very much for listening.